wouldn't have necessarily.
Oh, so it's Brian who we should blame.
So we should blame Brian.
Okay.
So thanks, Tony. You've got 40 minutes, and I'll wait
Sure.
45 minutes, and I'll let you know 5 minutes before.
Perfect.
Finish up then. Thanks. Okay.
Okay, then. I'll just get started. Again, there's no mic, so I just want to make sure you people up there can hear me okay.
Well, there is, but if you want to.
Yeah, I think if it's hearing okay, we can just go with it.
Yeah.
Close the door.
Okay. So I guess this is my first ApacheCon talk, and Mike strongly recommended that I should go. It's an amazing experience so far. I really like the conversational style of thought exchange that we have. And I might be the first guy to talk about Rust in this ApacheCon this year. So yeah, hopefully you enjoy this interesting story. And a little bit of information about myself. I'm a long-time Lucene user. There was past talks about what we do with Lucene in building buzzword. So basically we use Lucene to develop features that powers Amazon's search experience. Myself is a Rust enthusiast. In case you don't know, Rust is a programming language that is quite efficient and get a lot of tractions, ranked for many years being the most loved programming language for the Stack Overflow ranking, in case you didn't know. And I'm a proud parent for this cute little thing. Her name is Bounty. That's my dog. And let's start. Java is great, but why bother with Rust? Because Java, we can just compile it once and run everywhere. Like a lot of here are Lucene users. I think you already understand it very well across different machine platforms even. So it compiles, it works. And it's reasonably fast, and especially with recent JDK iterations. I recall like we stuck on Java 1.8 or Java 8 for so long, and then I don't know what changed. It just Java 9, 10, 11, we're at 24 now. So it's great. New additions have the all kind of new features. If you attended all the search talks, the most amazing ones that with recent performance-oriented thing are access to native memory, give you the SIMD instructions, all of that. And this talk we will talk about SIMD, so you can count on that. It's relatively simple, but really, especially with more than like modules and especially a lot of here are Lucene heavy audience, so I can just refer to specifics like we have to build for multiple JDK versions and release different kind of things. It certainly complicated the process of using it.
Hotspot compiler.
Yep. But nevertheless, it's simple enough, and it's a wide audience. So, and Rust, on the other hand, it achieves compile time, memory safety, and there's no GC. And it compiles down to native code, so there's no JIT, so you don't have the actual complication of a runtime optimization thing. And it supports zero cost abstraction. That means a lot, but in general, that means you are not paying for what you don't need. That means you can use different type in your program. You can wrap an integer and call it price, or call it mileage, and the type information will just come nothing at the runtime. So it's good for performance-oriented applications. But on the other hand, it's very hard to learn. This is top one complaint from the community. It needs at least several months of ramp up. But in practice, if you already have someone to lead you, that can be significantly reduced. And it has a long compilation time to figure everything out and optimize it. But the key motivation is just performance. I think within Amazon, it's also public. Around 2 to 3 years back, a lot of internal services got rewritten by Rust, and they see a nice performance boost, right? And then in the wild, we see things like a search engine called Tantivy, which come into our eyes, and they claim, according to their benchmark, that Tantivy is approximately 2 times faster than Lucene. And we're a heavy Lucene user, so it definitely caught our eye. And we want to figure out, is that true? Because we started out biased. We wanted Lucene to be faster, and so it's kind of hard for us to believe. So let's figure it out. And there are distinct communities. The Tantivy has its own community, and we have a Lucene community. I started off more familiar with the Lucene side because I'm a long-time user. So we really need a way to bridge them. And here is the Lucene util. That's the Lucene way to benchmark itself. It should be familiar to many of the audience here. And then we have this idea, just can we use whatever benchmark they claim and run the Lucene workflow, right? And specifically, that means we have the, I think it's skipping something. So, sorry. Well, the first thing we do is we ask the Tantivy benchmark repo to be open source. It didn't have a license to begin with, and then we wanted to do in open source, so we got it, and the author happily said, let's just use the most open source license.
And author was a creator of Tantivy? Was it Paul?
No, that repo is even inherited from some other guy. So this guy just have this framework of running different things.
Cool.
So we took Lucene util's large corpus, that is 33 million of English wiki serves. That's used by Lucene util in the nightly benchmark. And we looked at both engines, and we identified that Tantivy lacks a lot of exotic query implementations like geospatial queries or dimensional points. So we decided to just focus on simple things like lexical matching, term queries, and the Boolean compositions of them. And we collect top K or count exhaustively, or both top K and count. The difference is that more than Lucene executions allow skipping. So if you don't care exactly how many hits are there, if you just care top K, then Lucene can skip non-competitive hits as they collect the hits. So, and then we want to earn our benchmark trust. So I personally have a lot of experience doing that for internal projects, but the first thing is make sure we want to let the both setup return the same results. So that come down to do a lot of details. We want to sort the documents exactly as is on both sides, and we want to have same text analysis process. And also we want to apply some deletions because real world indices will have deletions, and deletions actually turn off some of the optimistic optimization passes in the code because handling with no deletes is easier. And for the query execution, we just want to measure for both setups what's the best case scenario for both. Right? That means we want to warm up the JVM as much as possible, both in terms of cold start or loading the index to RAM. And then we run web query at a time, and we take the best latency to represent how much time the CPU has to crunch the numbers to get things done. And turn out Tantivy is indeed faster, and we also got the attention of the author of Tantivy, Paul Mazur, and he had posts about it linking to our benchmark. And this is just a high-level view of the summary. So on the x-axis, it's just distinct query IDs, and then the colored dots are the latencies from both engines. You can see in general, the red dots are lower than the blue dots. That means Tantivy is indeed faster. So we want to understand, is it just the algorithm difference or just the language, the similar logic run in different setups are faster in one way than the other? So there's one algorithm difference example. So we noticed in the benchmark, that counting hits over disjunctive query clauses like A or B is much faster in Tantivy. And this led to our first cross-fertilization issue because Paul commented in one of the issues, since we have done this all in open source, it's actually in the issues of my repository. And he mentioned that as an optimization for count that can be used for Lucene, it first try to merge or union 2-bit set, then use the pop count, go through it, instead of going one doc at a time, which is Lucene's way, right? You advance this clause, this score, advance the other score, and you get one intersection at a time. That is going to be faster. So I have the links to the PRs. Well, it's not super useful. I wish I knew there's a better way to share the links. But it required API changes. It triggered discussions on how we should expose, instead of one doc at a time, but one chunk at a time, match evaluation. So first thing we need to do the API change, and then of course implement the pop count logic. For people who don't know about pop count, it's a very interesting algorithm that basically for common word lengths like longs or ints, 32 bits or 64 bits, you can get sublinear performance. Instead of shift ones and count whether the bit on the lowest or highest is one at a time, you can use basically less than 30 instructions to count that, to know how many ones are set in this single long. So it really helps in terms of if you have a dense bit set represent your hits, you can visually figure out how many ones are set that's equivalent to the count of the disjunctive case, right? And it turned out to be 20% faster for those verbs.
Sorry, modern CPUs have a dedicated instruction to do pop count, so it's even faster than the number of instructions you said.
Right. If our compilers are smart enough, I think even Java long exposed a pop count. I think reasonable implementation should be able to map to that instruction. And in the same issue, we have lots of scrutinies for the long-time Lucene devs. They look at our benchmark, they're trying to find errors, right? Although I'm biased for the Lucene community, but since Lucene results are not so super great to begin with, like they're questioning, okay, are we running some benchmark? Is the GC setting correct? It turned out that they are certainly. That's the power of open source, right? We re-scrutinized this and we did identify some improvements. It's raising the bar of benchmark trust even higher. So for example, we were asked to use more recent JDK version. And by the way, that was a time when we were heavily iterating, incorporating the Panama APIs and here and there, like JDK 19, 20, and then soon the 21. And also use a throughput GC instead of G1Ds. This is a bit counterintuitive because for almost real-world search applications, you want to use a concurrent garbage collector. You don't want pods. But in this case, since our objective is to measure the best case without GC even, impact of running just this logic at the CPU crunching numbers, so it turned out that we should use this throughput collector, let it pause, but hopefully across the many runs we measure, we get the best results. So we're, in this case, it's slightly giving an edge for Lucene, but we think it's accurate. And then we want to poke at language differences. So we want to compare, say, common CPU-bound work for both engines. Because the motivation is across the board, we know that it's faster, even for very simple things like term query, even a single term. And we know that, for example, they have similar data structure, although not exactly the same, but we didn't think, just by analysis, that it should be that much faster. So, you cannot figure more things on paper, so you have to figure out and do more experiments. So we have to dive deep into the posting format. I think for this audience, I don't have to explain this a lot, but the posting just a term matching to matching term map from term to the matching doc IDs. And they have similar encodings for the posting structure. And one of the things is the compression algorithm. So the compression needs to be lossless. That means we need to figure out exactly what are the doc IDs we store. And so the practical, by the way, the Tantivy engine is heavily inspired by Lucene. It's from its repo. So a lot of things you can expect to work in a similar ways, where before you write a segment, you actually sort those doc IDs when it comes to postings. So, and here are some specific just common integer compression techniques. One of the things is called frame of reference. It's just very simple. When you have a chunk of integers, this does not even need to work on sorted. You just find a reference point, and then take the deltas, and then you realize the max delta to be certain value, and you realize that it can be represented in smaller amount of bits. That's how you achieve compression. And similarly, you can have delta encoding example. Basically, you just take the delta from the current value and the immediate previous. So let's just go over quick because it's very simple. And the nice observations is if you have a sorted list, then you can combine the two. So you store a reference and then you further store the delta that give you even more compression. Both engine applies this technique, so we can expect that to happen. And then you see here we require only 4 bits when we combine both. Of course, you need some extra for the metadata. And then when you have this representation, you need to read and write in this short bits width to the actual, eventually to some persistent storage. So, right, it's not just on paper, you know the number, it's only taking that space, but you have to write it that way in a compacted format. So, actually Paul, which is the author of Tantivy, has this very amazing post on this topic back in 2019. That's way before our effort. Our effort was 2023. And this is bit packing with or without SSD3. So for people who are less familiar, this is one particular variant of the Intel SIMD instruction set released about more than 20 years ago. And SIMD has been there for over 30 years on PCs. And so it's surprisingly hard that not a lot of programming languages have good API programming model for it. We talk a whole lot on the Java side. It's still in incubating mode. And even Rust, there's no portable SIMD yet. To access SIMD, you have to use platform intrinsics, and that's platform dependent. So SSD3 specifically supports operating 128-bit registers. So that's for your common 32-bit integer. And then here's an illustration of how to achieve it. So here you see that white vacuum that just represents one 32-bit integer. And you fill it in. Here we're doing the big endian order, right? You just do this. And you fill this 2 bytes. But if you are doing the same way, right, here this is our 128-bit register, you actually will change the layout because you're operating same logic but on a wider register. So we're pretty much treating this as 4 integers at a time. So we will fill in the first half in one cycle or operation, and then fill in the other half in the next cycle. So you see the values up, the red, blue, salmon, purple, actually distributed across. It's actually a different on-disk representation, right? So this detail is important. And what's even more interesting is you can simulate SIMD, because especially Java, think about it, every modern Java release you have access to log. That's 64 bits, right? And you can treat it as two integers. So I'll just pause here, right? You can treat it as two integers and do similar trick from the previous slide. So instead of writing 16-bit value one at a time, you can carefully prepare a long with two 16-bit value, and then use that and treat it as a long to operate the bit AND or with the other long. So that's simulated simply. And this is a quote from the post. You can see, you don't see my cursor here, right? The fake SIMD has some fixed costs. Instead of doubling the scalar version, it takes some discount. Whereas the SIMD version, so it just goes linear 4 times, right? But this fake SIMD is still useful, right? Actually, Lucene implemented this. Lucene implemented this idea of int instead of long. But by the way, Mike, I think we should explore why don't we use long. But yeah, we see a good performance gain back in the days when we implemented this idea. So this is great. And what's the impact on actual queries? We benchmarked in my benchmark setup, because Rust is a native language. We can tell the code generation to not use certain features from the CPU. So here we tell it to look. There's the minus sign. Don't use anything beyond SSD. So the SSD 3 is 128, AVX and AVX2, and then furthermore AVX. There's AVX 512. That's just even wider register variants. We just want to disable it all, and we got this difference. By the way, in my previous slide, it's supposed to be an iframe to load the benchmark rendered website, and it sort of looks like this. Let me explain that a little bit. So we have the collection type. You see top 10 count. That means not only we want to get the top 10 scored, but we also want to run exhaustively. And then the type of query here, high term. You should be familiar with this since we ported exactly from the Lucene util. That just means we're issuing a term query with very high expected frequency. And you can see this pretty much are the common words. And Tantivy is very fast, so they claim it right about on average twice as fast. And we have another variant. We disabled SIMD, and we see the new average is around this value. So we pretty much observe around 10% of difference, if not more. So here, I'm just started to give you some magic or just a new perspective on different language and see why Rust can come handy when we try to implement this all bit packing. So this actual performance actually comes with a cost because neither language has a portable SIMD implementation. That means I cannot write a single piece of software that represents the algorithm and expect it to work in all kind of machines, operating system, right? And for example, this guy is an ARM-based instruction set. You also have a lot of x86. So what do you do about it? And so it's platform independent, as I already suggest. So Rust exposed those intrinsics, but still, you will have to implement your conditional compilation, etc. And here just a reminder of us that Java tries to solve this since JDK 17, and now 8 more releases down. It's still in an incubating mode. And just a reminder for features, you typically go through incubating, preview, experimental, and then stable. So we're here. So the thing is, you need fallback implementations. Let's say we compiled on a more than x86 piece of hardware, right? We write an index there, and given that they have different disk layout, right? But you run on a machine that doesn't have that instruction, what do you do? So you need to have a fallback implementation using the scalar operations. So that means you have to treat the word length as if it's an int4, right? But using your available instructions. So this is desperately in need for some abstractions, and again, we want to maintain the performance. Before we dive into Rust, the Lucene implementation is actually amazing. It's a fun story to tell, right? We implemented simulated SIMD with int32. That part is fine. We also use a Python script to generate Java code.
Who wrote that?
and why is that? Because in practice, you understand the algorithm pretty well, so you will end up values with different bit lengths. Maybe this block has a max value length of 6-bit, 7-bit, 12-bit, whatever, right? And actually, if you look at it, the block is fixed. Lucene, both Lucene and Tantivy fixed 128, right? So if you think about it, you pretty much already know which exactly bits to address for decoding ith value, right? So, and you don't want to write a generic function that says decode n, where n is a variable. So this is for some bit of actual performance. Lucene did it this way, right? And if you look at Tantivy's implementation, so here, if you don't understand this, it's pretty much fine, right? It's just trying to show you that in order to implement the algorithm, you need to have certain APIs, right? You need to, the abstraction here is, just walk over, the data type, right? And how to load such data, and how to store such data, and how to set a given value. Since we're dealing with integers, this doesn't have to be the data type, but just the integer. And then how to shift right, how to shift left, and then how to do AND and OR, right? This is the operations you need if we want to build an abstraction. And the implementation actually looks like this. So you can imagine somewhere down the road, there will be an algorithm calling this kind of API. So that means we can define another module that just fill in this blanks and you get another implementation, right? And Rust, well, this talk is not about Rust as a language, can give you this abstraction and compile down to very specific version of those types without runtime performance cost. So it also has a macro system. So I hope you're not scared if you ever work with C or C++. This is much safer macro instead of a very raw, just text expansion. You know, notoriously, if you miss a pair of parentheses, you get cracked. This is not the case, right? So it actually can expand for different SIMD implementations. So, and it can also use a macro to generate encode 1 bit, encode 2 bit, encode 3 bits, right? The similar problem that Lucene had to use a Python script to generate. So it's quite handy. And here's one, once you implement that generic thing, you just fill in the blanks, right? We have the block length, doesn't really matter. But here, you can rename those platform specific intrinsics. This underscore M112I, that means signed integer for the 128 wide register. You can just declare this and the rest works the same. And this will be the macro that declare the actual implementation, which itself is calls other macros. That's pretty much the plan we talked about in previous slide, right? And there's even more macro magics. Some enthusiasts, just like me, they implement loop unrolling. So that means because you know you want to just decode, say, 128 integers, right? Here we're using 32 to illustrate. So it can actually, at compile time, expand all of these. So pretty much, you see the const declaration here? You know exactly, not only is unrolled, so you know exactly which bits to go to unpack the next integer. So it's pretty amazing, and I'm happy to share that we developers can leverage tools provided by the language to do amazing things.
The macro at compile time is executing that for loop?
Yes.
Wow.
So basically, this kind of macro, I think we still have time, this kind of macro allows you to write Rust code to generate the Rust syntax trees, ASTs basically. It's not unique. Some other languages also has it, but this, because you can write the types safe, the type system is there to help you here and there. So you're not gonna just shoot yourself on the feet. So there's no runtime computation of loop-dependent variables. That's the benefit, right? So super fast. And another implementation or algorithm, language difference is this FSD. My colleague Anda already covered pretty much on this topic. Here is the FSD for a bunch of I think fruits, blueberries, cherries, and stuff. You can see the tail part get pretty complicated. It's sharing the suffix, right?
You have a dead state.
Dead state. Yes. So the both engines used FST to address term to the posting metadata, like where you resize on this, what's the offset, this kind of things. So we'll explore that. And this is the create from, not the creator of Tantivy, but another amazing developer. Again, if I have a way to share the slide, you can go to this post. It's amazing. It's very efficient to build FSDs. And Mike himself looked into this issue. He was amazed how fast this crate can build the FSDs. So it just implements a map interface from a byte to long. And it sort of looks like this. It just means anything that can be treated as a reference to a byte array, U8, and then the array syntax, I can insert that, right? This is where the Rust generic helps. Similarly on get, if you have any type, you implement how to view that as a slice of bytes, I can get a value back. So it's generic over input types. And on Lucene, we have FST-T, which is generic over the output. This is pretty amazing. Lucene has done great work to do that. And here's how it looks in Java. This is our familiar land. So, and then you look at this. The abstraction is pretty nice. We say in order to work with the FST, you have to implement this output type wrapped with your T. And this is because in the FST, each transition may have outputs. You know, not only shares the key space, it also compresses on the value space. So you're accumulating your outputs. So you need to implement comment or subtract, add, and then read and write just for serializing your value. And then when there's no output, you need to designate a special thing. So this is a pretty nice abstraction. But we have some long-standing issue like boxing. So that's a Java thing. So it just doesn't work well with primitive type. So I actually try to implement a more different posting format by mapping all the terms to its corresponding offsets in the on this representation of the posting. So effectively, I need an FST long, the primitive type. But here's the profiling output on allocation when I run on Lucene utils benchmark. You see, we have a lot of allocated value for just the long itself. And this is long-standing limitation of Java, not really Lucene's fault. And Rust generic works nicely because it takes a very aggressive approach. Basically, it's called monomorphization. So basically, bring everything into the single shape. That means it will instantiate the type and generate distinct copies of the code. And that's why, and one reason it takes longer to compile. And we have this project, Valhalla. It's trying to reinvent Java, basically. and it has primitive classes, universal generics. So I think we're counting on these to make at least the FST better. So here's a small teaser. I'll go quick. Give the crowd more time for questions. But there's a way to achieve branchless binary search. Right? It's also useful because once you decoded a bunch of doc IDs, you want to know like, where certain doc IDs are. Then you have to do this search. And I can tell you, this is branchless. You can copy this to Gopal using the latest Rust compiler. You will see the variants of conditional move instructions. So what is conditional move? It's basically CPU evaluates, especially for this short program, we don't have much set effect on both arms. It's just changing where the index is, right? It actually computes both arms. And then depending on the comparison outcome, it assigns value to a register based on the comparison results. So no branch, no misprediction whatsoever.
CPU never has to change where it's pointing its instruction decoding.
Right, and the cost is that you're computing on the other arm as well. But this is relatively cheap. We're just subtracting the indices. And I think Mike raised this discussion in the Lucene dev list, and apparently we have smart people like Adrian. He figured out that if you write your Java code this way, you will get branchless as well. But this is not a very conventional way to write binary search, right? You have to carefully think about it. But once you're into this mode, say, oh, this guy's only searching on 4 longs. I can do it for 128. But I think he claimed that if we write it this way, and he also verified the JIT compiled output, which I really appreciate he went down that far, and you will get branchless. You will get conditional move instructions. So hopefully you take away with talk, telling your friends you can do branchless binary search.
And there have been other branchless changes in Lucene, not just binary search, recently.
Yeah, you can just write your code in this style, knowing that compiler will rather take a simple compute to avoid the branching. So I think it's a general good way to optimize. But how reliable, predictable? Yeah, the miles varies, right? And it's especially hard on Java side to check the output. And here, I think I'll just have a quick summary about this work. So the Lucene community opened like over 30 issues related to Tantivy, and many of them lead to meaningful optimizations and get to Lucene 9.9 release. And Adrian was very happy. He made this post. It's claiming it's the fastest Lucene release. And also, Paul posted that Lucene struck back, and it's better, and it's faster for top paper. It's just really modest. We're still slower on some other type of queries, but it's an amazing cross-fertilization story, and it still continues. I think recently Adrian already opened another ticket or issue on the repo telling them our new way to encode postings. So it's really amazing. I enjoyed this open source participation, especially bridging communities is truly unique. So with that, I'll hand over to you guys and for more questions.
You've got 5 minutes left to talk.
Yeah.
No questions, right? So, yeah.
Lucene uses Panama to get access to the SIMD instructions, right? It's been in development for quite a while. I think one thing that maybe people didn't realize, the original, I think it was Robert who opened the Plan B. Does anyone remember the Plan B? Lucene developers got tired of waiting for Panama to fully incubate. So Plan B was, we have to start using it before it's done incubating, which is really hard because now we have to support multiple releases of Java, MRJAR, there's a lot of complexity around that. But that original inspiration that got Robert on board to using the experimental API was Tantivy.
Yeah. Because
that's what triggered the adoption of Panama.
Because after this one,
yeah.
In a word, competition.
In a word, Coopetition. Yeah.
Yeah. Healthy pressure applied from the other side.
Yeah.
Go ahead.
Oh, I was going to bring up more on the Valhalla because it's still just the primitives we haven't seen quite yet. Generic primitives. Because I thought unboxing was in 25 as a preview.
Oh.
Maybe we're getting it soon. I'm not staying on the very top. Actually, I just did my research on Valhalla. I realized, oh boy, it has so many things. Right?
Yeah, 24 and 25 have been an impressive set of releases for getting as far along with Valhalla as they have.
Yeah, I think there are two parts. One is the how you express your logic to work on primitive types. Also, sometimes you need to have certain complex type, but they're all made from primitives. Can we avoid paying the cost of the object overhead? I think that's another thing to make things even more faster.
So that would be an interpretation of the new record type that gets introduced with Valhalla as well, which basically decomposes the classic object without the pointer into a set of primitive fields. And so you lose a lot of the object overhead in JVM, and you get the, not quite all the way to arrow, but a lot of the value of just, oh right, in memory these are just a bunch of records of the same set of fields.
Correct.
And I believe they're all represented as primitives, so you lose a lot of overhead when it comes to objects.
Yeah, so that's why I think we can count more for Java to happen. How long does it take? Don't know.
Records are already there. They've been there since 23.
Yeah, we use records, but
Record
17?
Yeah, is that 17?
yeah, but the primitive.
I know because I'm using them.
Yeah.
We're still at 17. Me too.
Okay.
Yeah. So we use records, but I don't think it addressed in particular the primitive part.
Right. No. Records isn't right. It's unrelated.
Yeah.
I've got a sort of a silly question, which is, so Tantivy is a new thing for me. It's similar functionality to Lucene, but are there different use cases for it? Is it people use it purely for the performance? Could you use it as an OpenSearch to replace Lucene if you wanted more speed in OpenSearch? They're almost random questions. I'm curious. So.
Sure.
That last question you asked was what inside Amazon kicked off this whole comparison
Oh,
of
really?
Tantivy
Okay,
and
right.
Lucene.
Yeah,
Could we
okay.
replace Lucene in OpenSearch?
Right.
The gist.
Oh, there we go.
Yes.
Yeah.
Silly question.
It's a good question.
Good questions, right? So it can be its product segment. It is trying to compare Lucene as an engine, right? So you can implement things like Solar. Actually, they have a closed source product called QuickWit. It's more equivalent to Solar, and they got acquired by Datadog years back. And Lucene is still functionally very rich compared to Tantivy,
Right.
but they sort of shines in terms of efficiency. The one killer app they have is to index a whole lot of the logs, and in a very efficient way
Right.
for both querying and storage.
So maybe the question is, could you use both Lucene and Tantivy in OpenSearch? Different.
I'm not
Different
OpenSearch
workloads.
expert, but I hope I think they have ways to hook things in. Yeah, like if you want, you can
Cross-language.
even do with the remember their FIAS talk. Like you can implement the Tantivy codec, but the thing is, yeah, you can definitely can. I will not just go into the technical details, but you certainly can.
Right. You might be able to get a codec, like have Tantivy write the index and make a Lucene codec that is binary compatible at read time, perhaps. So could maybe use Tantivy for indexing and Lucene
Right.
for searching.
Takes so much work.
So much, and
Yeah, but maybe it's faster to index in Tantivy.
on that topic, I'll just throw out one thing. So try to search for Rusi. So basically replace L with the R. That's, I think, from a Chinese company called Zhihu, trying to implement an older version of Lucene, 8 point something, purely in Rust. It's trying to, the approach is taken is trying to go for the same design, same like index searcher, all the hierarchy that we have, but re-implement in Rust. They got it working for one version, then
It's incredible because it's
Then-
so hard to import that much code. It's so
Yeah.
complicated.
and then discontinue in maintaining. If someone's really hyped and trying to do this, they can certainly do it because there are prior examples.
Yeah.
Yeah, I can have 14 Lucene don't have different methods.
Yeah. So we wished for a binary compatible like index format from both sides, and we can maybe indexing using one and search using the other one, just get best of both worlds. So it's possible. I think that's why we're here. It's open up possibilities.
Tony, you said in passing that Lucene should look into doing the fake SIMD on long,
Yeah.
encoding 2 and 32s, and that we already do it for an int, but we don't do it for long in Lucene? Is that what
Right.
you were
But
implying?
basically, it comes down to the container size. Right now, we use 32. So
Okay.
for like 4 bits values, then we can do this, right? I think we have no reason not to use long.
Have you opened an issue for that?
Not yet.
Yeah, you should open an issue. So it would apply for cases where the SIMD Panama path isn't working out, like it's not using SIMD instructions properly. We could fall back to that.
Yeah.
Yeah, you should open an issue.
Sure. I think, but yeah, last question.
Okay, yeah, the last thing. Remember from the earlier talk, right? You were chatting and I was chatting about the FST and the postings format. I was pointing out that our sandbox, that it was pointed out there, it's very relevant here, it should have been brought up, that the postings, the entire term dictionary in Tantivy is in an FST, unlike Lucene, which puts, only half of it. And yet, that Lucene, nonetheless, with its richness, which I think is a strength, really, we've got sandbox postings formats out of a whole bunch of them. And one of the which does maybe the same thing, kind of, sort of. And you pointed out that the distinction, though, is that the FST postings format puts the entire postings also embedded as the output, which is probably not a good idea. So maybe that could be. I would wonder. I think it's an area for Lucene to potentially improve. Is consider a new FST postings format with only the long output, so that the postings don't have to go into FST as well. Granted, you want the so-called pulsing, which is the single doc ID pointer.
Yeah.
You still want that, though.
Isn't that what your PR was?
Yeah, I think I will share my PR with you. That's basically
Cool.
the idea.
Oh, I'd love to see it.
Yeah. And this is not merged in, but it's halfway there. The only blocker I think is it doesn't do well on certain fuzzy queries and stuff.
Okay.
Because what I found is intersection between the FST and the automaton representing the query constraints are not very efficient because of the memory accessing pattern of the FST.
But for non-multi-term queries, maybe it's better.
Yeah, primary lookup sped up like 25%.
So that's awesome.
solid.
With per field postings format, you could use that for your primary key. Use Lucene's
Right.
default everywhere else.
There are lots of people that don't use multi-term queries, or only the prefix, which is like a special case to count.
Why was it not merged? Are there bugs in it still, or it just lost
No,
attention?
It just lost traction, I
Yeah,
think.
you should go like bump
Yeah.
it. Put a comment on there saying, especially if it's sandbox, like the bar is low. If it's working,
Sure.
make
Yeah.
it an option for people to play with.
Yeah, I can share you very quick after this time. So
Yeah.
thanks for the questions and thanks for staying late.
Can I say one more thing? For those of you who want a nice chuckle on your Sunday evening, I highly recommend reading the first cross-fertilization issue, the link that Tony put in there, because you see a fun interaction of the personalities in Lucene, like Uwe, and the personalities in Tantivy, like Paul, as they totally talk past one another, trying to reach some consensus on what is actually happening here. It was sort of the first contact between these two communities, and it's really hilarious. There's an accidental typo, there's a discussion about the typo, there's a correction of the typo that had another typo in it, and then there's a discussion. It's like two conversations happening simultaneously on that issue.
Yeah.
It's really hilarious to read. I reread it last night and laughed. It was really cool. It is, yeah. It was something. Tony, did you open that issue? It was Tantivy does this awesome thing. Why aren't we doing it in Lucene? The first sort of inspiration of what we could improve
Yeah, I
within
think
Lucene.
you opened it like why optimize count implementation in Lucene. and
Okay.
then cross-reference the issue.
Right.
Yeah.
Okay. So it was the first thing we saw that that's a great idea. Why is Lucene not doing that? The first algorithmic kind of improvement.
Yep, I think we're officially out of time. Feel free to hang around and chat and ask further questions. Thanks everybody, and thanks again for the speaker. Thanks Tony for being the last speaker on the last day.
Yes. Thank you.
This is the issue.
Yeah.